All right, I think congratulations on everybody passing the banquet test. The first lecture after the banquet.
Well, it's now that maybe young people don't remember, but that was always the most respectable position at any conference. The first speaker after the conference dinner.
Yeah.
So, of course, Professor Okounkov.
Thank you. So I'll start with maybe explain. So some remark about the previous lecture is that I may have slightly oversimplified the life. So if we have this G equivalent cohomology of some space X, maybe call it AI. These are in real life. So in real life, they are not given as cohomology. It's cohomology of some complex. Like, for instance, we talked about K groups, and we divide them individually, not as cohomology of some complex. But still, they fit in this pattern, which so if I have a cone of a map, so I have cohomology, so if I have X going to Y, going to the, so maybe a map F, there's a cone of F. So this is what should happen is that after the H cohomology of Y maps by pullback to the H cohomology, maybe ith cohomology of X, and there's a map again by pullback to the ith cohomology of the cone. And there is a map which shifts cohomological grading by one. So they fit in this long exact sequence. If I have a cone of complexes, then the cohomology form a long exact sequence. So that's what we were using, not the fact that we had when we did the computations. We used the fact that this fit in a long exact sequence, and that's so. It's a general remark. Now go back to our order of the business is to compute. So maybe I remind you what was where the end of the lecture found us last time is that we had some a unitary group of some vector space V is naturally acting on the projectivization of that space V, and we would like to know what is the U equivalent K theory of that projective space. This is complex vector space. And what we did is we took this vector space, maybe call it again. Now this is our space V. We can think of the projective space as I take the sphere here, maybe I'll just write S, and I have to mod it by U1, or maybe S. This is sphere dimension, well, if this is of dimension N, this is a sphere of dimension 2n minus 1. And this quotient is the projective space, and this fits in this exact sequence when we have the sphere, we have the disks that fill it, and we have the corresponding, so there's a disk, and when we take the disk and collapse the sphere, that we get the top space. So it's an example of that. Right? Yep, makes sense? And now, what's the relation? What's the relation of this cohomology of the projective space? Well, if I have, as we discussed last time, if I have free quotient by a group. So if I have, in general, if I have G equivariant theory of some space X, and if G acts freely, X has free action, then to give a vector bundle on X is the same as to give a vector bundle on, just really take the quotient. And so maybe I'll skip one. If I apologize if this complicates the video process. So if I want to know U equivariant cohomology of the projective space, that is the same as UV cross U1, where this U1 is the center of this group. So they together act of that sphere. That by this principle. That's clear. Generalizing this principle, so generalizing the principle, suppose the action is not exactly free, but suppose I ask myself, what is the G equivariant K theory of a homogeneous space? What does it mean to give a equivariant bundle on a homogeneous space? Like imagine I have like an actual three-dimensional sphere, and I want a bundle which is equivariant under all rotations. Then it's enough, so maybe I'll have to draw it a little smaller. Where's the eraser? Let me try a little smaller. So suppose I want a vector bundle on a sphere which is equivariant with respect to all rotations. Then I look one point. One point is fixed by rotations here. So I have to tell you how this stabilizer of a point, how its action lifts to the action on the fiber. Right? So if I tell you how the stabilizer of a point acts on the fiber, then there's a unique way to extend to the action on the group on the whole homogeneous space. That clear? So this means that this is the same as just the action of the group on the fiber, that is to say, the H equivariant homology of a point. Right? Which is concretely, what is it? This is representation. This is the ring of representations of the group. So you can think of this as kind of integer valued functions of an element H considered has to be mod conjugation. And what does it mean? So what does it mean, the integer valued function invariant under conjugation? It means integer linear combinations of characters of reducible representations. So this is Z, means Z linear combinations of the characters of irreps. And so for instance, if the group is a circle, then this is just like a Laurent polynomial with integer coefficients. So now with this, we want to write the long exact sequence for this inclusion. So we have so let's for simplicity, let's denote this whole group G. Then we're going K not G of the sphere. There is a map by restriction to K naught of G of the disk. There's, by definition, there's a map from K naught G of the corresponding Thom space. So when you take the disk and you collapse the sphere. And in principle, there are connecting maps. We'll We'll discuss the connecting maps in a second. So in principle, there's some kind of connecting maps here. But what is this? What's written here? Here we have so what's written here? Here, this disk, that's contractible. So this is just the action there is the same as action on a point, on the center of the space. So this is just the representation ring of the group G. Right? And this is a homogeneous space. A sphere, the group acts transitively, so that's a representation ring of the subgroup, which the subgroup is the stabilizer. So if I have a point, so I have some point P, I have a group acting, this maybe G, maybe I'll write G, stabilizer of a vector, of a non-zero vector, GV. So I have some point, and there's a stabilizer of that, so the GP, the stabilizer. This is H. Now, and what's this? Yeah. Term of the inclusion. So this is inclusion of the. So this is a trivial vector bundle over a point. So we take this vector bundle, we contract infinity to one point. Right? So this is the term space for the. So this okay, all right. Thank you. This is the term space for the inclusion of 0 into the total space of V. So we take the V, we contract to the point. So what is this? This is the interesting part. These are what's by definition here? These are representations of G that are trivial when restricted to the group GD, which is. So what's the group GD? The group GD, it's the group where I have to fix some vector. So maybe I have some matrix with some eigenvalue, maybe A1 or maybe, and then some matrix G prime, and then I have a variable T, and this satisfies the condition that A1 times T equals 1. Right? So when they both together act together, so they have together fix a vector. So one can scale a vector. So this has to be a vector which is eigenvector with respect to this. With the eigenvalue with this has to do with this. Right? That makes sense? Right, so what fixes a vector under this action? It has to be an eigenvector for the matrix here, and this has to be the eigenvalue. Or the inverse of the eigenvalue. That everybody agrees with that? So these are functions on the group G. So I'll just write I'll write R. These are functions on the group G modulo conjugation. And these are functions that vanish when I restrict to the subgroup. Okay. Which functions on the group G vanish when I restrict to the subgroup? Well, that's just what is the locus of those matrices that have an eigenvector? That's the study in linear algebra. So this is naturally identified by what? By this is to have an eigenvector, it's a codimension one condition, and given by, so this I'll write it like that. So what's that? this is all possible function times the equation of having an active vector, means the determinant of 1 minus Tg. If this determinant vanishes, then this matrix has an eigenvector, and this is the inclusion. That makes sense? So, and now to continue with the long exact sequence, we see from this that this map is an inclusion. That's injective. Therefore, there's no connecting map here. This thing is 0 because that's K-theory of a point. So this is an inclusion here. So there's no map coming this way. This is 0 because it's K-theory of a point, and so therefore this is also 0. So the K-aught is 0 in this sequence. So in principle, there's a connecting map. We don't know, but since this is injective, the map from here is 0, and this is 0, so this is 0, and similarly the other way. So K-aught of a point is 0. Aught cohomology of a point is 0. Right? Group element. So G is in UV, and T is in U1. It's this element, G. What? G is an element in my group. So it's elements in K-theory, their K-theory of a point are functions on the group. So you can evaluate a function. It's natural to give if you want an element in K-theory, you give a conjugation invariant function of an element of the group.
You say odd, but sounds like O. K-O, whatever.
It means knockout, right? KO, is that? Yeah, look, okay. So this is to finish. So what do we have learned? We have learned that if I take UV equivalent cohomology of projective space, this is equal. You take K UV of point. I join one element with the relation T plus minus, and this becomes this guy. This would be the line bundle O of 1 on this projective space. And the relation is that the determinant modular condition, determinant of 1 minus Tg is 0. Clear? G is an element. So this is what? These are functions. This ring, these are functions of an element G. If you have a coordinate here, and here's the coordinate G. So the elements in K theory, they're functions on a group. So if you wanna write an element in K theory, you just write a function of a group. So this we've written function on product of two groups. Yeah, it's right. Modular conjugation. Okay? And this you can do, when you do this Tom computation, you can do it in stages. And so if I compute the Tom space, you can add Tom space to Tom space. And that has, you can do it. Here we had, so this says that if I don't consider the whole group U of V, but take a subgroup of the form inside here, if I have V decomposed into V1, V2 plus something. So I can a subgroup which is the product of smaller unitary groups, then I can do the same computation in stages, and I get the same answer. But it's just the conjugation will be with respect to a smaller group. That clear? The answer is just the same. So in particular, if I'm interested in torus equivalent K-theory, so in particular, an example of that is I have just the diagonal matrices, product of U1s. So this would be if I'm interested in torus equivalent cohomology of projective space. But it's the same thing. It's the functions on a torus. So I'll write in Laurent polynomial as A1 plus minus, A2 plus minus, and so forth. These are Laurent polynomials on this torus T. And then I joined one more variable T. And I consider the equation that the product. So this equation then becomes the product of 1 minus T times AI equals 0. That clear? That's the same. So if you want the algebraic, you have an algebraic GL and topological, the corresponding compact, that's the same. Because for many reasons. Like topologically, the reductive group contracts to the compact group and so on and so forth. So that's okay. So now let's go back to this, revisit this computation from the point of view of what we were doing last time. Last time I drew this Kazul complex. So what is this? This is what I'm trying to say, that this concrete representative of this relation, or maybe the concrete representative of the relation, better, more factorially if I write, I apologize, if I write T inverse G inverse, of course the same equation. This guy here, this equation, that is the Kazul complex. These are polynomials in. This is supposed to be a function on a product of a group and one more scalar, and invariant under conjugation in the group. And the condition is that the scalar is basically it says that this scalar is an eigenvalue of an element in the group. That's a polynomial with integer coefficients, this. Or equivalently is this. But this is a little better because it's actual representative of the Kazul complex. And why is this? Because right, we'll do the resolution. So we'll just compare with this in a second. So what was the so this is I it's always good to take a break in the lecture and draw the table of all monomials, which I always never miss an opportunity to do this. So the table of all monomials is x1, x1 square, x2, x2 square, x1, x2, and so forth. Maybe x1, x2 square. And so, what? Yeah, there are many pictures that we'll keep for the next lecture, yeah. So this is what you're trying to say. We're trying to take this function 1 as a module over all polynomials. That's the skyscraper. That's the it's kind of like the delta function at 0. It's the skyscraper sheaf at the origin. It's something on which this is by definition this whole I don't know, right, Z. Since we're doing integer coefficients, let's do Z. This is mod, or no, we're doing sorry, I forgot. We're doing complex vector bundles. Got carried away. Sometimes I get carried away in the lectures, I apologize. So this is complex. So this is polynomials modulo the ideal, which the ideal is the ideal generated by x1, x2. So this is the red, in red is the ideal. If we wanted to write a resolution of this structure sheaf, well, how we go? We start with this structure sheaf. By definition, that maps x1, x2, which is what? These are functions. This is polynomial functions on V, right? And then the kernel of that is generated by x1 times functions plus x2 times the functions. And then, and so this would be, I take this picture and I subtract what's generated by x1 and also subtract what's generated by x2. But then I subtracted what's generated by x1 and x2 twice, so I have to put it back. So I take this guy and I have to put it back. So this would be x1, x2 times cx1. And this would be exact. So this is, if you compute the character of what we're doing here, this would be, this is what's written here. So this is, if I look at this as elements, if you pick this, I consider these guys as elements. So I view the terms in this complex, I view as elements in this case, K, say U2 cross U1 equivariant cohomology of the vector space. So what's it going to be? Here sits nothing. It corresponds to trivial representation. Okay, this says 1. So here I have to subtract, and I subtract what? This x1 and x2 are a basis. X1 and x2 are a basis in linear functions. Right? So linear functions is V is a representation. Linear functions of V form a dual representation. So I subtract. So I have. Sorry, I apologize. I can't write formulas from the side. Resolutions from this side is fine, but formulas from this side is bad. So I'll write 1 minus. So I have functions dual representation, and in particular, how is the center is supposed to act? The center acts by scaling on the space. On the dual representation, it will act by inverse scaling. So this would be T inverse. And then what's written here is the wedge. So this will be plus wedge 2 of the dual representation times T minus 2. So if I compute the character of the space, so this is, if I compute the character of the space, I get what? So if I compute how an element G acts in this representation, well, it's going to be 1 minus, so it will be the trace, in the dual representation, trace of G inverse, times T minus 1, plus this will be the determinant of G times T inverse. This whole thing is the determinant of 1 minus T inverse G inverse. Okay. So this element here, this particular polynomial, this slightly better polynomial, that actually represents a very specific element, very specific generator in here, namely this Kazul complex. G inverse, yeah, a determinant of G inverse, because dual representation is that. There's a unity of math, yes. Yeah, but it's so maybe Vanya is making a good point. There's this kind of there's a funny relationship between topological and algebraic key theory, and sometimes they very closely related, sometimes they diverge, but they're certainly very closely related for a point. So any representation of a compact group is holomorphic. So this is and so any spaces that are built for points in some very simple ways, they inherit spaces that build from points and representation in some kind of ways. They inherit the fact that the topological and algebraic key theory remain closely related. In fact, sometimes the same. Yeah. Sure.
So then it will be reported through informal algebraic. What about topological part of the story? For arbitrary V, which is for young.
This is for any V. For any V whatsoever, yeah. So if for any representation, that's still the same. So it's just if what does it mean have representation? Representation have some subgroup in here. Right? So here's with respect to all things, and representation means I choose a subgroup in here. Yes, please. Where? Here? There? But it's just if you think what is these are functions on a group that have to become zero when restricted to a certain locus. And what's the locus? The locus is locus of matrices that have an eigenvector given with this eigenvalue. Right? Well, because this vector, so this is, what is this, what's the sphere? The sphere is a homogeneous space. And what is fixed as a point? The fixed as a point, I have to first have to be, this point first have to be an eigenvector with respect to this group. And second, its eigenvalue has to be this, or inverse to this.
So there's another choice.
Say it again?
So is there any other choice of that condition, like A1 divided by 2?
Well, I don't know. Maybe we can talk a little more. I think they're all equivalent. But so this is, of course, as an equation of the group. This defines this. If T, since T and G in invertible, this equation defines the same locus. However, this is a particularly, you can say this is a particular nice section of the corresponding line bundle. Right? Okay.
Still, for our representation, Kazul resolution will be exactly more complicated. And then the right side, algebraic, will be different.
I think, Banya, I think what you're saying is that of course you can take some number of copies. So what you can so you could be Trudy. What you're talking about is this. So if I have a tensor U v1 product U v2 embeds into U of v1 tensor v2. Right? You agree? And so if you take this subgroup, you're going to get your Jacobi-Trudy form. So this is the Kazul resolution is completely canonical, is invariant under all possible groups. In particular, if you have any representation of any group, the Kazul resolution will be Kazul resolution. That good? So so I have to look at my notes. Where was I supposed to say next? There's so many things to say, but maybe. I'm not sure what's the best way to proceed. Maybe I'll say a few words since This course is supposed to, this course was supposed to get to elliptic cohomology at some point, right? So maybe it's a good way to say what is the analog of, while we have this formula on the board, what would be the analog of elliptic cohomology analog of this formula? So and we can before we talk about general group, let's fix some so let G be a compact group. E.g., G could be U1. Let's start with U1. It's, I think in topology, in some sense, everything else. So in representation theory, there's many interesting groups, but in topology, in some sense, this is the most interesting. So this is then we the U1 occurring K theory of a point. This is the representation ring of the group U1. That's the same as integer valued polynomial, integer coefficients maybe in some variable t, just like we discussed it last time. And this is, you can think of this as well, these are trigonometric polynomials on the group itself. We have this, we had obviously, so elements in K theory of a group, you should really think of functions on the group. And what they are, if you think of a group as S1 or R mod Z. In this realization, these are trigonometric polynomials with integer coefficients. So, that makes sense? And so, right, or also Laurent polynomials on C times. That is to say, this is what dot C times. C times is the complexification of my group. So then you would like to say kind of elliptic U1 or point. Well, you would like it to be elliptic functions or some functions on elliptic functions on your group U1. And so this is we'll get to that in a second. So, or that is to say functions, i.e. functions, these are holomorphic functions here. So these are functions holomorphic functions on C times we take mod powers of Q. A holomorphic function invariant with respect to Q. Now anybody says there's none such. There's no such functions. There's no non-constant function. And that's actually can be important when you think about. So one important property of Krichever genus, key property proven by Krichever, is rigidity. And in the end, it reduces the fact there's no holomorphic functions on this elliptic curve. But that's not really an obstacle, because remember when we talk about, well, I don't know, maybe whether you remember or not, I'm going to remind you, is that these equivariant cohomology groups of X, they should take values, they can in principle take values in vector spaces and so forth, but they have to take values in some category where exact sequences make sense. So instead of saying these are more, so instead of saying that these are, so what does it mean to say equivariant K-theory? So every equivariant K-theory group is a module over equivariant K-theory of a point. So everything is a module over this ring. But it might as well be a sheaf of modules over some global objects. So they may very well take values in sheaves. Well, in this case, coherent sheaves. Sheaves of over something. Could switch on something. So in particular, in this case, they might be for elliptic cohomology. So H, whatever it is, elliptic, whatever it is, may very well be, this could be a sheaf. This really could mean a sheaf on H, G elliptic point. Or just write, maybe I'll write elliptic. G for U1, for G equals U1, this is a sheaf on elliptic curve. In other words, say it one more time. K-theory, equivariant K-theory is a module over a ring, namely the equivariant K-theory of a point. Module over ring is a special case of a sheaf on an algebraic variety. It's just your algebraic varieties are fine, and the sheaf is given, well, it's just a module over a ring. But if algebraic variety is not affine, like the elliptic curve, makes total sense to say this cohomology should go to a sheaf somewhere. It doesn't have to be a vector. So cohomology doesn't have to be a vector space. Can be a bundle over some other space or a sheaf on some other space. It's kind of an important point. In other words, the values here, it's okay for this to take values not in vector spaces, not in modules over some ring, but in vector bundles over something else, or somehow sheaves over something else, in particular sheaves over the elliptic curve. That makes sense?
What do you mean by elliptic functions?
Well, a meromorphic elliptic function, that's easy. It's a meromorphic function here. So it's easy to say what's a meromorphic. We don't want to be, here we don't take rational functions, we take polynomials. But we could have taken rational functions. And then the analog would take meromorphic functions here. And that would be just meromorphic functions on this elliptic curve.
But it was a good point.
What?
Quite a big question, right?
Well, I don't know, I mean,
There was a ref U1 before, and then you changed it to elliptic function.
Yeah, we can bring Katz and Moody later, so let's just. Yeah. And let's just then go through what I've written so far. Let's go through that same computation with this new so this is maybe easier to start with this one. So if I'm interested in, what's the elliptic analog of this computation? Okay, maybe as much. Nikita, I may have to erase this table. Yeah. Oh, okay. But there'll be some other pictures that somehow you can use. Yeah. So what's the analog of that? So if I want elliptic, maybe write first elliptic torus equivalent cohomology of a point. Well, if I have for U1, so if this is a product of U1 to some number R or N, if for U1 this is supposed to be an elliptic curve, well, it makes sense that this, of course, would be E1 e to the power R. So we're not talking about rings. We're talking about the objects that the corresponding rings define. So a ring is the ring of functions on some algebraic variety. That algebraic variety you can consider. This, if you take a non-affine algebraic variety, there'll be no ring of functions. There'll be sheaf of functions. But this is the algebraic variety. It's like this. This is that. And then elliptic covariant cohomology of null projective space. This is what? This is you take this guy here, cross one more elliptic curve. So this is you add one more variable. And inside here, so maybe this is some. So what does it mean? What does it mean I have take a quotient of a ring? That means the corresponding algebraic variety embeds the other way. So I have R copies of elliptic curve cross one more copy. And then said here I look at the locuses where one, if I have coordinates AI here and a variable t here, I look at the locus as one of the AIs is equal to T inverse. Okay. This is, I use the equality and I use the inversion in elliptic curve. It's a group. I can not just or make sense? That's the locus in here. Yeah, they're all the same. Yeah, Q is always fixed. Yeah. Elliptic curve is always fixed. And now you see that this thing is invariant. So there's an action of symmetric group, which is the Weil group, of here. And so this locus is really descent, or it's a pullback inside. You look at unordered R tuples. So this is ordered R tuples, and you can consider unordered R tuples, cross one more of them. And so there will be the locus of the same, they're really the same equation. Defines it here. And this is naturally because this is, what's the difference between here and here? Here I have eigenvalues ordered, and here is eigenvalues go unordered. So this is the current UV current K theory of P. Yes. This definition, yeah. Well, definition is something else, but this is the result of computation. The computation is the same. Because what we used in the computation, what we really used in the computation, that if I have homogeneous space, so maybe I should say it. So now it's going to come rather close to Nikita's lectures, but maybe I will be a little sloppy in terms of identifying the exact nearest point. But Nikita maybe help me. So this is the how one way, if you're more familiar with Nikita's lectures, maybe one way to think about this is the following: so if I maybe so how how am I supposed to think of so maybe I'll look at. So let's just go back to that. What I was alleging here is that the UR equivalent elliptic cohomology of a point, that should be like the R-fold symmetric polarly coelliptic curve. So it's unordered tuples of R point on the elliptic curve. You can say it's a definition, yeah. But anyhow. But you still want to think of this. You still want to think of an element here. It's kind of like an element in the group. So this is sort of like, there should be some kind of map from the element of the group to here. And what is this map? When I write an elliptic curve, so what's an elliptic curve? If I identify the unit circle with some, so I glue the unit circle to some so if I glue the variable, the unit circle z equals 1, I glue to a variable. Usually people prefer to have q less than 1, so I do it the other way around. So if I have a q less than 1, so this is my variable q, and what I do is I glue the unit circle z equals 1 to the circle where the absolute value of z equals the absolute value of q, and identification is multiplication by q. That's the elliptic curve. And now if I have an element in the group G, I can form a vector bundle on the elliptic curve by saying, well, I'm just gonna I look at the sections of this vector bundle where the solutions of the equation f of qz equals g times maybe this element g times this element f of z. In other words, any element in the group defines me a bundle on elliptic curve. And this is clearly it's only up to conjugation. This is some kind of map from the group, or rather even classification of the group, to degree. So this is the degree of that bundle is 0 because the transition function is constant. So it's a degree 0 bundle. And so this set is really equal. These are semi-stable degree 0 bundle on E of R of semi-stable GLR bundles. This is for any group you can define something like this. For any group you can consider its classification, and you can consider the corresponding bundles on the elliptic curve, and then by using your group element as a transition function, and that would be like a map from the group to here.
Andrei, I'm confused a little bit. No, that's as functions, only the functions, right? Is it exactly what you're saying, right?
I'm saying what I'm saying, and you're saying something else. But so in Nikita's lectures, you've seen pictures like you go around. So I apologize. You kind of, I don't know you've seen picture like you go around a circle, and you experience a monodromy G, right? This is the analog of that one dimension down, and then you also already had an elliptic thing, or yeah, there was also, but in one dimension down for K theory, you can think of K. So in other words, so to make not to confuse people too much, just make some kind of connection, and we can talk about it. Make connection. What Nikita was explaining, that if I'm interested in K theory, recurrent K theory of X, there's some sort of relation between this in cohomology of maps from S1 to X. And with cohomology, equivariant X mod G, but this is equivariant with respect to rotation. Rotation of Q is an element that rotates this S1. So Q here, you should think of an element of absolute value 1, and it rotates this S1. And in particular, when what does mean you go to a quotient, and you closed loop may very well end not in your original point, but a point that changes by G. And similarly, if you go at one dimension up, and Nikita, I think I must have annoyed him by asking him questions about his lectures, but anyhow, you can one dimension up, the analog of that, you can have a situation, so you can have elliptic cohomology of X has something to do with the equivariant, again, with cohomology of now maps from actual elliptic curve to X mod G, where this elliptic curve is in the spirit of what we did here. Elliptic curve. Look, this is. I don't want to be precise about it. Yeah, I'm just saying that this is, you can interpret computations in this thing as computational elliptic cohomology, but you don't have to. It's much easier to work with what I've said, because here, elliptic curve can be any curve whatsoever. Like, for instance, it could be a curve over a finite field. I mean, you study cohomology with finite coefficients, no problem. If you have a finite coefficients over a finite field, you can have a very interesting elliptic curve. It somehow makes no difference whatsoever. Yeah, doesn't have to be presented in this way. Yes. Every elliptic curve is hyperelliptic.
Central board.
Yeah.
There is a ref at least 3 times. Ref. You need to put representations of something.
No, but this is what is rep. Rep is so your original. So okay, so this is your group modular conjugation. So okay, this to answer your question. What is your group modular conjugation? Group modular conjugation. So if I think of this object as bundles on elliptic curve, group modular conjugation are similar objects, but now when your elliptic curve is singular. Because if your elliptic curve is singular, just take P1 and glue 2 points. Then so the analog of that, this is like when Q is actually, so this corresponds to Q actually equals 0. Right? So elliptic curve is singular, then you have a bundle on P1, but you have to identify two endpoints. And this identification is a group element up to conjugation. So, and similarly, if you study bundles over nodal elliptic curve, those are naturally the Lie algebra of here. So if you think of it, what does it mean to define a bundle over nodal elliptic curve? That's naturally the Lie algebra of your group modular conjugation. Right, cuspidal, right. So this is the group, and this is the Lie algebra. This is nodal curve, yeah, and this is cuspidal, yeah. Well, if you think of it, so if I have a cuspidal cubic and ask what's peak of that? Peak of that are additive group of the field. Because so what does it mean? If I take the normalization, then the functions would be functions without linear term. And when you take modules over that, you can specify the linear term arbitrarily. This linear term in your function, that's what defines bundles. So this gives you, okay. So maybe I try to say if you think that the analog of group modular conjugation, so if bundles over nodal elliptic curve is group modular conjugation, then bundles over actual elliptic curve, that's kind of like elliptic analog of your group. So now to What?
If you take not UFD but real group,
Uh-huh.
what is the cohomology of rigidity? We'll come to this.
It's
We'll come to this.
no. It's good. So this is a really good question. So what? So I'm hoping to get to this question later in this talk. So if there's somehow enough. So but before we yeah, we still need some general pieces of the story to put in place, and that's a general statement about Thom isomorphism. So if I have some space X, then and I consider a vector bundle, some vector bundle. So maybe I need more space. So left. So I have some space. So I have some space X. Oh. Apologies. So let X be like that. And I consider some vector bundle V over X. So then so this is a complex vector bundle. All right. Then what Thom isomorphism says that if I take the Thom space for the embedding an X into this total space of vector bundle, that this is supposed to be the equivalent K theory of that is supposed to be isomorphic to, by Thom isomorphism, supposed to be isomorphic to the equivalent K theory of the space itself. And you can imagine and in fact, so what was the definition of that? These are the complexes of vector bundles on some neighborhood of X. So this is by definition. Complexes of vector bundles on a neighborhood of zero section that are exact away from the zero section. And we have a canonical element here, namely the Kazul complex. The Kazul complex is written completely in terms of a vector space. If I have a vector bundle, then I have the exact same thing, just fiber-wise. It's a complex that is exact away from the zero section. And the statement of Thom isomorphism is that, in fact, this guy is if I have a complex, you can tensor multiply it by anything you want, and this will still exact. And so then this guy is a generator.
This doesn't depend on the effect.
What?
It doesn't depend on which fiber bundle you take.
No, it depends. Depends. It's for every fiber bundle. So let me just say, maybe this is better to say is a rank 1 free module over Kx. And this is a generator. And using this generator, you can in principle identify the two spaces. And to say it slightly differently, you can consider there is an inclusion. So you can ask, there is an inclusion of the zero section. So there's a map iota inclusion of the zero section here, so you can ask what's the pullback of this guy. So if I take the map K theory of the Thom space and map it pullback under the inclusion to the K theory of X, then the image of that goes into this Kazul complex times here. So this is maybe for reasons that I'm going to explain, I'll call it theta. So this would go into theta times K of X inside here. So this is not the Kazul complex. What's it going to be? The Kazul complex. You're gonna it's some complex. You pull it back, you get this expression. We have it somewhere on the board. Namely, this theta is the alternating sum minus 1 to the ith. Hold on one second. So this is the theta of v. I'm trying to motivate the good reason to call it theta. Right? So theta is just, so if I have a vector bundle, I can form this expression, which I want to call theta. And then this is the general feature of total isomorphism, and you can imagine how this goes. We did it for one point, but the argument was completely general. So if I have some bundle over some base, it's going to be the same. That this guy goes in here, and it generates the ideal spanned by that theta. Right? And what is this? So this is this. This guy here. And what is this guy? So like we did in the first lecture, any bundle whatsoever is pulled back from, so this is maybe a bundle, vector bundle of rank, let's say of rank R. And so this bundle is always pulled back. This is a map to what? Map to this B U R. So this is the Grassmannian of R-dimensional subspace and infinite dimensional space. Over that, there's a tautological bundle. And this class, so the bundle itself is pulled back, and the class, therefore, this theta of v, so maybe we had this gamma, and so this class theta of v is the pullback of this kind of universal theta, which is we essentially computed. That's the if you think of this as this was the this universal thing is if you need to write. So what's a universal bundle over Grassmannian? Universal bundle over Grassmannian is just it's just kind of universal bundle with fiber CR. So this is if I think of xi's as the Chern classes of that, or whatever ai's, so this is a product of 1 minus ai inverse. And it goes from 1 to r. This ai's are so this is so those are the Chern roots. These are the Chern roots of universal bundle. Well, because we want, this is the reason. So if we want to we want to normalize things so that the Kazul complex represents the resolution of the structure sheaf of the zero section, and that resolution goes in dual spaces, not. Okay. And now I now want to look at this formula and interpret it in terms of in the terms that we have there. So this is what, if I think of, in general, this is what, this is the equation. This equation says that one, a matrix has a fixed vector. The matrix fixes a vector. If AIs are the eigenvalues of some matrix, as the equation says, the matrix fixes a vector. And then in terms of vector bundles on nodal curves, what does mean a matrix? Matrix is a transition function that tells you how the section goes from here to there. What does it mean it fixes a vector? It means the corresponding bundle has a section. And the analog of that in elliptic cohomology is that you have a theta divisor inside R tuples of symmetric curve. This is given by saying that this is one of the numbers is 0 or origin. And in terms of the corresponding bundle on the elliptic curve, it says this bundle has a section. This is kind of an important notion in integrable system. Many spaces in integrable system, they're moduli of bundles or something somewhere, something. And then in moduli of bundles, we often have canonical divisors. Canonical, not in the sense that canonical divisors, they're distinguished divisors. That's formed by those objects that have an extra section. And that means some determinant vanishes or something like that. And this is called the theta divisor in general. An example of that the theta divisor on the elliptic curve itself. That's the only, the zero. It's the only degree 0 bundle that has a section. And the theta divisors that was in Sam's lecture, those are formed by degree G minus 1 bundles that have a section. And in general, and if you have a particular section of that thing, which is usually given by some determinant or theta function or something, that's the tau function. So all I'm trying to say that if you want to define, there's an analog. So the moral of that story is that, not the moral of the story, it's an important point. The important point is that the elliptic analog of this story is in some ways similar, in some way not. It's similar in the way that there is a, so to speak, isomorphism for elliptic cohomology, which just says that if I study the elliptic analog of this object, this has become, so if I study in elliptic cohomology, this is still rank 1 module, which is not free, it's locally free. It's kind of an important thing. So so we're talking about global objects, then it's okay to have things which are locally free but globally non-trivial. So it's a line bundle over that. And what is this line bundle? The Stone class is pulled back. So So elliptic Tom class is pullback of this class under the classifying map. Exact same thing. The main difference is that the Tom isomorphism is not an isomorphism. It's saying that some object is local, is a line bundle over, you have some things over some base, and locally it's isomorphism, but globally there's a non-trivial line bundle. And what does it mean concretely? So this says, so there's a, so if I, in other words, if I consider the corresponding pull-bell MAC in elliptic homology, that's going to be not, this will be, but no, just be saying, so what does it mean in K theory? In K theory it says there's this goes, so in K theory that says, that goes to polynomial that vanish when this goes to the polynomials that vanish that one of the eigenvalues is 1, right? And that's same kind of thing, except the polynomials that vanish were one of, so what I'm trying to say. So this is, I'm trying to say something very, very simple, but it's important. So if I look, so what does it mean concretely? Suppose I have a product of theta of AI. I goes from 1 to R, right? That's kind of like, that's a function that vanishes exactly when one of these variables is whatever, 1 or 0, depending how you denote the origin of the elliptic curve. But this is not a function. This is a section of a line bundle. And concretely, this is not an, if you, what does it mean? If you change the periods, if you shift AIs by Q, this will produce a non-trivial factor. So this is concrete manifestation of that. If you write formulas in elliptic cohomology, these formulas in general will have theta functions in them. But this is, theta function is not a function. It's a section of a line bundle. And the meaning of that section, all these line bundles come eventually from the fact that this defines a locus where one of the things is 0. That's a non-trivial divisor in the product of elliptic curve. It defines a non-trivial line bundle. Make sense? So now that we have a Tom isomorphism, we can define So Kazoo complexes looks like, so this expression, so in theta functions you will have, so what's a theta function? Theta function looks like 1 minus, say, z inverse. Well, this is how Sam wrote it, something like that. And then product over n goes from 1 to infinity. You put 1 minus q to the n z, 1 minus q to the n z image, right? This sort of thing, right? And so this is, you should, very good. So this is so to speak kind of like the actual Kazoo complex, and this looks like some sort of correction, which you think about in terms of what I was trying to explain there. This looks like a Kazoo complex on loops to X, because if Q is what rotates a loop by some parameter, this looks like a Kazoo complex. But it starts with this. And so this is the important part. This is what defines. So now we have to define push forward because this is so
excuse me. Do you hear me? I'm curious. Is that the divisor? Sorry, the line bundle which determined by the theta divisor is just determined by the elliptic curve?
Maybe I can answer this question in 10 minutes because I need to really finish this topic. We need to somehow, there's some curriculum we have to cover. So the Tom isomorphism, like I said, it's a wrong way map. So if I have some x that sits in some ambient y, and the normal bundle to y in x, if this is complex, it doesn't have to be holomorphic, it just has to have a complex structure. Then y, just because we can, Thom space is obtained by some sort of collapse. As we collapse, if we have more points in y, we can collapse those points. So y maps to the Thom space of x embedded into. And so then we have, that says that the K-theory of y, there's a wrong way map, the first push forward map from the K-theory of x via the Thom isomorphism. This defines the wrong way map. So this is very easy to explain in terms of algebraic geometry. If x is a holomorphic submanifold inside a holomorphic manifold, then I can just take the structure sheaf and just push it forward. Just really embed. But this is, if you're interested up to some stuff, this can be said topologically. That's the way to say it. And this is a wrong way map and has the property that if I push forward and pull back, that's multiplication by the Thom class. And so if I push it forward by Kazul complex, pull it back, then I just get the class of the Kazul complexes. And now if I have a general map, is called complex oriented. So now suppose I have a general map. What? Oh, the normal bundle. Right. Thank you. So a general map from x to y is called complex oriented if I can take x, maybe this is y. What? Thom class. It's also this is the Thom class. So if I have a general map called complex oriented, if I can realize it as an embedding like that, follows. So if I take some kind of bundle, might as well take trivial. So maybe I take a trivial bundle over y, and I want to embed x in a way just like I did into the trivial bundle. Then I take, then by this kind of collapse, the Thom space of the embedding of y into this trivial bundle, just no, y into the trivial bundle. So I embed y into a trivial bundle, and so this maps, because I can, if I want to collapse more, this maps to the Thom space of the embedding of x into its normal bundle. Right? Because what's a Thom space? Thom space is I take everything which is away from the zero sections and I collapse it all. Right? And so in particular, if I collapse the infinity of this space, I can collapse more and have this map. So this map, then the pullback under this is functorial. And by Thom isomorphism, this is kind of like K-theory of y, and this is K-theory of x. And they map the other way. So you have a push-forward map this way. But so this is, again, if we're talking about maps of algebraic variety, this is the definition of algebraic geometry. So what's it mean algebraic geometry? Some map, you can embed your x into, I don't know, maybe projective space across your target. And then you first push forward to that projective space, and then you push forward along the projective space. That's that. So for algebraic variety, it's the old definition. It just says for general things, for general maps, map is called complex oriented if it has a structure like that. Any two structures like that, you can, if you take the product of these two graphs, you can homotop one to another. So any two structures define the same map. So maybe I'll say this one point. It's kind of important thing. In algebraic geometry, one can really push forward things. Just if I have a subvariety that defines me a coherent sheaf on the ambient space, and that's the push forward. And if I have a sheaf on some variety, and it, the variety maps to a point on some other variety, I can push forward that sheaf. And so this requires just really, but this you can say, to say this, it's enough to know just the tone isomorphism. If you have this normal bundles that have complex structure, then you have this map. But then so this is, if you unravel what this thing says, so if you unravel, if you denote so if this is my map, x goes to y f, we divide the normal bundle to f to be the normal bundle to x in its embedding minus this Cn. And this is right. Again, if you really have a normal direction that you add, if you want to use tone isomorphism one way, you multiply by theta. If you want to use tone isomorphism the other way, you divide by theta. Then the corresponding elliptic thing says that if I take the theta bundle of minus the normal bundle of f, and this is a sheaf on kind of elliptic homology of x, this maps to the structure sheaf of elliptic homology of y. In other words, you don't go from functions to functions. There's a twist by theta functions, which is this. Because if you push forward one way, you multiply by theta functions. If you push forward, if you use tone isomorphism, any use of tone isomorphism means you have to multiply or divide by theta functions. And so this is, here you first use it one way and then in reverse. So you multiply by by one part you multiply, by the other part you divide. Yeah, make sense?
Normally this sheaf on k elliptic of x related, right?
No. So there's some. This is elliptic homology of x. That's some scheme.
Yeah, scheme over E.
Scheme over whatever. Yeah. So this is on that scheme. I have a line bundle, and that maps there.
Everything are schemes over E, not over some.
No. It could be over whatever. So over k crank homology of a point. Could be some whatever that base is.
But this means that k tone is some red one sheet over k of x, right? Local, right? But anyway,
Yeah.
So, good point to stop.
Let me. Yeah, maybe this is all I had. So there's many more things in my notes for today, but I think we're probably going to get to them tomorrow.
Postpone them for tomorrow.
Yeah.
Okay. Questions. Actually, there was one unanswered question.
Yeah.
You pointed about trivial group.
Oh, right. So this is the So this is, we'll get to that so this is where we're planning to get to that in I have so if I have homomorphisms of G1 to G2, homomorphisms of groups, then bundles, G1 bundles over E map to G2 bundles over E. That makes sense? So that is to say that elliptic G1 equivalent cohomology of a point, it's a scheme, maps to elliptic G1 cohomology. For instance, if if G1 is the trivial group, then its image is the trivial bundle. And morally, if I want to reduce the group, I just pull back things more. With cohomology, all operations with cohomology you have to do in some cohomology of some complexes. So all this operation you have to do with some portion of derived pullback. But if you do suitably derived things, if you just pull back under this map, that's your. So if you want to do non-equivalent cohomology, well, you have a trivial group. Non-equivalent cohomology means a trivial group. Whatever you had before, you pull it back. And as a preview, sorry, I apologize, a preview for tomorrow. Remember the equations for K-theory of projective point space? Was the equation, was the product of 1 minus T inverse AI inverse equals 0, right? What does it mean to take it non-equivalently? Non-equivalently means set all the variables A to 1. And then you get just 1 minus T inverse raised to the dimension of the projective space equals 0, which is true equation for the case here of the projective space. Just because the generator is the same Kazul generator, the same Kazul complex, still the generator. It's just you forget the equivariance. Yeah. Do you have a question? Okay. Exactly, yeah. So this is so.
So when I make an elliptic cohomology with C star, I get less than C star. But if I take the secret group, I get more than the group. That's perfect.
No. This is so. Actually, you should think. No, that's not right. No. So the control question is you think they in. So okay. So maybe we'll take this kind of question. GL. Let's say. Stable or semi-stable GLN bundles over E, or in fact, on an anywhere curve, that's by Narasimha-Seshadri, right? That's the same as UN bundles over. Yeah, look, Vanya, we're in overtime right now. So what does it mean? This means for UN bundle, maybe so flat UN bundles. This means what? That means for a bundle we have this means maps from pi1 of E, which is Z square to UN, right? So this is the way we think of a. It's a kind of non-holomorphic way to think about elliptic curve is in fact as a pair of commuting elements. So similarly here, so you think of this, you can think of this kind of holomorphically or thinking non-holomorphically. Now if you think non-holomorphically, an element an element in elliptic cohomology, a pair of commuting elements. So, for instance, if I take a cyclic group, pairs of commuting elements in a cyclic group, there's a n-squared torsion point in the elliptic curve.
Okay. So are you satisfied? So you already started tomorrow lecture, yes?
Yes, exactly. But
now it's a good point to take a break.
Yeah.
And the speaker. And now there is some other announcement from the.
Yes, please, let's take one more quick group photo with people who joined us this week and without people who left us this week. Okay? So it will be the same place on the stairs just outside the building and coffee break right after.